Anybody understand what I just asked? Vn dot Vn. Well, there is no n. It's just V. Because remember, V is the vector whose components are V1, V2, Vn. So the dot product is just between V and itself. So this is another way to define. You see how this becomes a bit more complex now? Instead of finding the square root of V1, V2, V, like the way we've normally defined, we can now define the norm as the square root of the dot product of V with itself. And connected to this is what is the norm of V squared. So if I square both sides here, what do I get? I get V dot V. This becomes very useful, notationally speaking. So we can go back and forth between norm and dot product. So I just good to keep in mind. Okay. Okay. So of course we have properties, right? We have properties to the dot product. So if we have the vectors u, v, and w in Rn, and c is a scalar, then we have the following. We have the property that u dot v will be the same thing as v dot w. I mean that u. You can think of this as a symmetric property or commutative, right? It's commutative because multiplication is commutative. So let me ask you this. Can you guys prove this? Can you show this? It shouldn't be too much. And I think we need a bit more practice and exposure to proofs like this. This is like little proof. But how would you do so? Anybody have an idea of how do we start a proof for something like this?
Could we do like a proof by induction?
Yeah, this has a proof by induction feel to it. It does, but it's a bit simpler than induction. You can apply induction, but it's a bit simpler than that. So embedded in this is kind of saying, okay, if I am in Rn, right? What dimension is it? It doesn't matter as long as it's some dimension. So that's where the induction kind of is hidden inside. But let's suppose I'm in Rn, wherever that is, R10, R15, R20, R100, R2, R3, it doesn't matter. If I'm in there, then what do I know? I know that What else? Let me just say, yeah. I know that U is U1, U2, U3, isn't it? That's the way we define what U is. It's an arbitrary vector in R, pardon me, Rn. So there should be a dot, 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 Un. And V is another arbitrary vector in Rn. So it has some component, right? So it has n components with some numbers in them, whatever they may be. And then what is U dot V? What is U dot V? Well, isn't it U1 times V1 plus U2 times V2 plus U3 times V3 all the way to UN times Vn? And if you want, you can rewrite this in shorthand notation as I goes from 1 through n of U sub I times V sub I. But by what? By what property can I change this order? By the commutative property, right? So by the commutative property of multiplication, I can write this as Vi times Ui. Not a big deal. I can switch this around. The commutative property of multiplication. And now what does this become? This becomes V1 times U1 plus V2 times U2 plus Vn times Un. But what is this also written as? V dot U. So what did I just show? I showed that this left-hand side here is equal to the right-hand side. So I'm done. Put a little box with it with enclosed with shaded inside. Means end of proof. Not a really complex one, but just the idea of how to show something is true, particularly in linear algebra. I show that the left-hand side of this equals the right-hand side for any arbitrary vector in Rn. So this will work for any. Do you guys see that? Again, it's kind of a bit straightforward because it is straightforward because it's expected due to the fact that commutativity of multiplication between two numbers. It follows. What's another one? If I have U and I dot product it with V plus W, this will equal what? U times V plus U times W. So what do we have here? We have a distributive property. So dot product obeys the distributive property. Do you guys see how the proof will go? What will be the proof of this? Also pretty straightforward. We let U be the same idea, right? U1, U2, UN. Let V be V1, V2, Vn. And let W be W1 all the way to Wn. I want to show the left-hand side equals the right-hand side. So what is the left-hand side? What is this? Well, this is U1 this is a U1, U2, UN. I'm dot producting this with what? V plus W is what? it's V1 plus W1, comma, V2 plus W2, all the way to Vn plus Wn. That's what V plus W is. And then when I dot product this, what do I get? I get U1 times V1 plus W1 plus U2 times V2 plus W2, all the way to UN times Vn plus Wn. And then what do? I can distribute this U to each of these terms inside, can't I? And so this becomes U1 multiplied by V1 plus U1 multiplied by W1 plus U2 multiplied by V2 plus U2 multiplied by W2 plus all the way to UN Vn plus UN Wn. And then what can I do here? What should I be able to do? I can group all the ones with the U's and the V's together. So U1 V1 plus U2, U2 V2 all the way to UN Vn. I can group all of these together because of commutativity and associativity of multiplication and addition, right? So because of the it's because of the commutativity of addition and the associativity of addition, I can rearrange the order of the addition and I can group them together. And by the same token, I can do this as well. U1 W1, U2 W2, all the way to UN Wn. But then what is this here? This is the dot product of U with V. And what is this one here? That is the dot product of U with W. And I just showed that the property holds. I showed that this here left-hand side with some algebraic steps, simple algebraic steps shows you that the right-hand side holds. And so we're done with the proof. So all of these kind of properties here that we come across, they're able to be proven. That's why they're called properties, because they're true. So I'll give you a few more, but I won't prove all of these. So this is K, I should say C. C, if I multiply it by a scalar and I dot product two vectors first, this is the same thing as saying, first apply the scalar multiplication of C and U, and then dot product that with V. That's also true. And V dot V is greater than or equal to 0. And V dot V is equal to 0 if and only if V is the 0 vector. And again, you can apply the reasoning that V dot V, what was the V dot V again? V dot V is the norm squared. So remember the properties of the norm. So this number 4, this property here follows from the norm being non-negative, and the norm only being negative of a vector if that vector is 0. So this is just stems from that definition. Okay. Okay, guys. So that's a few of the properties for dot products that hold. So again, the dot product V dot W is equal to V, the norm of V multiplied by the norm of W multiplied by cosine of the angle, or V dot W is equal to the summation of VI times WI. And I goes from 1 through N. So that's the two different ways for dot products to be defined. Sometimes one definition is more convenient than the other. And we showed that how these two things are identical. Now, what's good about this definition is that you can actually define the angle as a dot product. So by doing some algebra here, what else can I say? I can say that the cosine of any angle between two vectors, the angle between any two vectors is equal to the dot product, which from here I can define using this definition. So the dot product of V and W divided by the norm of V multiplied by the norm of W. Or I can go one step further and say theta is cosine inverse of V dot W over the norm of V times the norm of W. So we can actually compute, we can calculate the angle theta between two vectors V and W. Okay, so this is a special little formula here. Now I'm gonna take a little more attention though. Give a little more attention to this one. Now recall, what is cosine bounded by? What is cosine always between?
Is it adjacent over hypotenuse?
Cosine is adjacent over hypotenuse, but what number is cosine always between? So Gershon, that's right.
Yeah.
Gershon says -1 to 1. That's right. It's always between it. Now, we just defined cosine of theta to be what? I can replace this as V dot W divided by the norm of V times the norm of W. So what that tells me is that this product and division quotient, this dot product divided by these norms always will be between -1 and 1. And on top of that, I can rewrite this double inequality as the absolute value I can rewrite this double inequality between these two numbers, 1 and -1, as the absolute value. So the absolute value of this guy is less than or equal to 1. Is the same thing as saying this. It's the same. Of course, this is already non-negative. So I can rewrite this even further. So a lot of this stuff is rewriting. I can rewrite this even further as the absolute value, not the norm. This is not the norm. This is the absolute value of the dot product divided by the norm of V multiplied by the norm of W is less than or equal to 1. And where am I trying to get at? Where am I trying to get to? What I'm trying to get to is the following. From here, I can say that the norm, that the absolute value of the dot product is less than or equal to the norm of V multiplied by the norm of W. And this, my friend, is one of the most, I would say, iconic inequalities in mathematics. This is called the Cauchy-Schwarz inequality. Cauchy-Schwarz. Like two very famous mathematicians, particularly Cauchy, French mathematician. This is called the Cauchy-Schwarz inequality. And you can also rewrite this as the fact that if you take the absolute value of the dot product of VI times WI, this is less than or equal to the square root of V dot V multiplied by the square root of W dot W. And if you want to write this in terms of summations, you can write this as VI squared, I goes from 1 through n, raised to the 1/2 power, multiplied by the square root, the summation from I from 1 through n of WI squared, raised to the 1/2 power. So this here is the Cauchy-Schwarz inequality. Okay. Very important inequality, not just in linear algebra, but in other other realms of mathematics, real analysis, complex analysis. Okay, so now that we have the dot product, and we're learning about different ways of defining the dot product with cosine of the angle, and now with this addition of multiplication of products of the components of the vectors, and how from there we can go into this inequality called Cauchy-Schwarz. Now let's see a bit more of a geometric understanding of norm. So again, recall what happens when you add two vectors. So if I have, for example, a vector like this, I got U, I got V. So if I call this U and I call this V, I would call this U plus V. Right, adding two vectors. So when you add two vectors, this is what I get. I get a triangle. Now, does anybody remember what the triangle inequality state? Remember the triangle inequality? This is a property that every triangle must hold in order for it to be a triangle. So you see how we're going from algebra to geometry, we're just bouncing back and forth. So does anybody remember what the triangle inequality states? Anybody? No? Okay. So the triangle inequality is the fact that the sum of two sides of a triangle must always be greater than the third side. So if I take two sides of any triangle and I add those sides up, it will always have to be bigger than the other one in order for it to even be called a triangle. Think about if that weren't the case. Think about if you had two sides of a triangle and it was not bigger than the other side, then you would never be able to connect and form a triangle. So then how can I represent that using vectors and using norms? So what I'm saying is if I have the length of u, which is the norm of u, and I add this to the length of v, then what? Then this must be bigger than the other side, the length of u plus v. Now you can consider the case of equality, even though it's not common to see a triangle flattened, right? So if this was equal, if u plus v equals u plus v, then you have a triangle. It's called a degenerate triangle. Not that it's bad or anything. It's just that it's a triangle that has three sides, yet it's kind of a flattened line. But this here is one of the properties of norm. And it stems from the triangle inequality. So this is called the triangle inequality for vectors. So vectors also abide by the geometric principle of the triangle inequality. So how do I prove this? How do I prove this to be true? And again, this is so the thing that's going on here is that we're kind of going from R2 and R3 space, finding things out in R2 and R3 space, and then just extending that to Rn. That's what we've been doing since we've talked about vectors, right? We know how to treat vectors in two-dimensional space, three-dimensional space, and then we say, you know what, in four-dimensional space, we just add one more component. We add one more coordinate. In fifth-dimensional space, we add one more, and so on. In n-dimensional space, we have n of those components. When we talked about the norm of a vector, we said, oh, the norm of a vector in two-dimensional space is the Pythagorean theorem, v1 squared plus v2 squared. And then you're like, oh, in three-dimensional space, it's v1 squared plus v2 squared plus v3 squared. And then you say, oh, so in n-dimensional space, it would be v1 squared plus v2 squared all the way to vn squared. So we've been going from R2, R3 to Rn, R2, R3 to Rn. This triangle inequality is really just for R2 space. And what we're saying is we're extending this idea in R2 space into n-dimensional space. So that's the little jump that's not seen. So we're going to say let u and v be in Rn. So again, this is just like the motivation. This here is like the motivating example for this property of triangle inequality for vectors in Rn. Now, how do I prove this in Rn space, not just in two-dimensional space? This is already covered in triangle inequality. We just apply the triangle inequality, it's always true. But how are we so certain that this triangle inequality also holds in n-dimensional space? That's why the proof is necessary. So all we have is that Rn, that u and v are in Rn. So the trick behind this is if you start not with the norm of u plus v, you actually start with the norm of u plus v squared. You start with that first. Now, why do I treat this first? Is because when I take the square of a norm, I get rid of that square root. That square root problem, that little square root symbol can be a nuisance when we talk about proving things. So if I square this, what do I get? I get u plus v dot product it with u plus v. I get the dot product, remember? The norm of a vector is just the dot product of itself. Especially when I have the norm of something squared, I get rid of that square root. So I have a dot product. By the properties of the dot product, what can I figure out? How do I dot product the sum of two vectors? Well, I can apply the distributive property and I get u dot product with u plus v dot product with u plus v. And I can do this again, right? I can do u times u dot product plus u dot product it with v plus v dot product it with u plus v dot product it with v. But then one of the properties that we saw is that the order of the dot product doesn't matter. So I actually have this. I got u dot u plus 2u dot v plus v dot v, right? Again, what am I trying to show? I'm trying to show this. I'm trying to show this. So I have to have norm again somehow, right? I have to get the norm symbol pop out somehow. And where does it pop out? It pops out with these dot products. What is u dot vu? It's the norm of u squared. And what is v dot v? It's the norm of v squared. Now, what do we do here? Now, the key is there's something called the Cauchy-Schwarz inequality. And what does a Cauchy-Schwarz inequality state? It states that u dot v is always less than or equal to the norm of u times the norm of v. So that means that this thing here will always be less than or equal to what? The norm of u times the norm of v. And now what do we have on this side now? What do we have? Can anyone tell me how I can rewrite this? Norm of u squared plus 2 times the norm of u times the norm of v times plus the norm of v squared. How can I rewrite this? No? Nobody sees it? How do you factor this? What does this a squared plus 2ab plus b squared factor into? Now we're talking, right? Yeah. This becomes a plus b parentheses squared. So I know because you see this new notation, you might be like, wait, but how do we deal with this? Think about this, guys. All of these things here are constants. You can treat this as a, this becomes a, this is b, this is b. So what is this going to turn into? It's going to turn into the norm of u plus the norm of v squared. And so now what did I just show? What did I just show? What I showed was that the norm of u plus the norm of v squared is less than or equal to the norm of u plus the norm of v quantity squared. And do you see why it would make sense to have it squared in the beginning? Because now when I take the square root on both sides, what happens? I get the norm of u plus the norm of u plus v is less than or equal to the norm of u plus the norm of v. End of proof. A very standard proof, but it's very nice, right? It's algebraic, but it's nice how you can use algebra to in a way manipulate things so that you get your desired statement, mathematical statement, which is the triangle inequality for vectors. And we applied this very key inequality, the Cauchy-Schwarz inequality. Okay, so now we're heading into the world of linear algebra that relies much more on proofs. We've seen linear algebra from a more computational perspective, right? We've been dealing with system of equations, knowing how to apply row operations, understanding how matrices are linear transformations. We had a little bit of proofs, but now it's much more necessary, much more ingrained in this side of linear algebra. So linear algebra is both very theoretical and extremely applicable at the same time. So it's a broad range. Okay, so we'll end today with the last 10 minutes with a very key topic that truly is ingrained in mathematics, which is the idea of orthogonality. This idea of being perpendicular, being orthogonal, is, since the ancient times, people have been considering this, interested in perpendicularity, being perpendicular, having vectors that are perpendicular. So orthogonality is related to being things that are perpendicular. So recall in the two-dimensional space, what does it mean to be perpendicular? Perpendicular lines form what? Form 90-degree angles, don't they? So if I have, now instead of using lines, what am I going to be using, guys? What terminology?
Planes.
I have two vectors. What if I have two perpendicular vectors? What's the angle between them? 90? So the angle between these two vectors is what? 90 degrees. But where does this 90 stuff come from? Where does this angle stuff come from? Remember dot product? What do you guys remember about dot product? The dot product between V and W is what? The norm of V times the norm of W multiplied by cosine of the angle. What's my angle here? 90. What's cosine of 90? cosine of 90 is? It is what? You guys should know this at the top of your head. If you don't remember this, you should remember the unit circle, 90 degrees. The cosine of the angle is the x coordinate. It is 0. So what does this tell me? The dot product of two perpendicular vectors or orthogonal vectors is 0. That's what I have. That's very important, guys. So the dot product of two perpendicular, I should say orthogonal vectors equals 0. Okay, makes sense? Very important. A very important statement. The dot product of orthogonal vectors equals 0. And this idea can be taken and developed into when you guys learn about lines and planes and how to find the equations for a plane, and you talk about the normal vector, you talk about two vectors, like all of that is embedded, is based upon the fact that the dot product of two vectors is 0 that are orthogonal. So piggybacking off of this idea, we care a lot about what are called orthogonal projections. So that's when we have, again, this idea of having a vector and we shine a light above it, right above it, right? And then this casts a shadow of some sort where it's broken up into two vectors. And these two vectors are perpendicular. So if I call this V, let me call this W1 and call this W2. The idea is that V is the sum of W1 plus W2, where W1 dot product with W2 is 0. Okay. And now I'm gonna do one more thing. Let's suppose I have a vector that's a scalar multiple of W1. In other words, there is some vector A, right? That if I multiply by a scalar, I'm gonna call it C, I get W1. So I'm gonna rewrite this just for rewriting purposes sake. V is equal to C times A plus W2. I think that's the way, yes. So there is some vector that's a scalar multiple that if you take the scalar multiple of A, right, you make it W1. And then you have W2 that when you add these two vectors together, it gives you V. Now, look what happens. Look what I'm going to do. I'm going to multiply both sides by A. Dot product it with A. And when I do that, what happens? I get C dot A plus W2 dot A, and I get V dot A. Now, because A is in the same direction as W1, then A is also perpendicular to W2. So this guy here is equal to 0 because A is perpendicular to W2. So what am I left with? I'm left with V dot A equals C multiplied by A dot A. But what is A dot A? That's the norm of A squared. And what am I looking for really? I'm looking for what is that scalar? What is the scalar multiple that I need to give to A so that I get the W1? And what is that scalar multiple? It's V dot A divided by the norm of A squared. So what is W1 then? Remember what W1 became? Remember W1? What is W1? W1 is C multiplied by the vector A. But what was C? C is V dot A over the norm of A. And what we're going to call W1, we're going to call that the projection of V along A. That's what this stuff is here. This is called the projection. So W1 was a projection the whole time. The projection of the vector V along the vector A. So this is the formula that will be used to find the vector, the projection of any vector along any other vector. This is the formula. Okay, so we'll talk about that next time. We'll finish up with some examples of how to apply this formula.